Given a graph, a cycle is a circuit with no repeated edges. So for instance, in this graph, a circuit, let's say around E, with no repeated edges could be this, 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 this. So that would be a cycle. Another possible circle would be this, 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 this. So any circuit with no repeated edges in the graph is called a cycle. And a tree is a connected graph with no cycles. Amongst the set of all graphs, the ones that are trees are going to be very important, especially in computer science. So let's examine these three graphs that we have here and see if any of them is a tree. So let's look at the first one. Is it a tree? So we have to see if it contains any cycle. You see that, any path that we can do here is going to be always open. It's not going to be closed. It's not going to be a circuit. So this one is going to be a tree. This one is a tree. So let's check the next one. What do you think? Let's look at for a moment. So we can easily see that this one is not a tree because we have, for instance, this circle is contained in this graph. Or, say, this cycle. And let's look at the last one. So what do you think about this one? Is it a tree? So we can see here that we cannot find any cycle in this graph, right? So this one is going to be a tree. Also, both of these graphs are connected, right? So that's the condition. Have to be a connected graph and have to have no cycle. So because of that, these two are going to be trees. The connection condition, actually, if we drop that condition, we have this other definition here. A graph not necessarily connected with no cycles is going to be called a forest. So, for instance, if we consider the set of just these two graphs that we have here, set the first tree like this and this other one, we can say that this set, the two with the two components, let's say, this is a forest. So a forest is something that the connected components are actually trees. So this series of results that we see here are going to characterize completely what a tree is. So these 5 conditions are equivalent. In particular, we see that to be a tree is the same thing that saying that for each pair of distinct vertices there exists a unique path between them. What does it mean? That between 2 points in a graph in general we can go in different paths. Well, if the graph is a tree, we cannot. The only way to go between 2 distinct vertices will be just one way. So, for instance, in this last tree, if we want to go from here to here, let's say, the only way to go will be this, this, this. There is no other possible path. Check all the possibilities and you will see that is the only way. Instead, in a graph that is not a tree, so for instance, in the second one, to go from here to here, we see we have more than one way. We can go like this, or we can go like this, or even we can go like this. So there are more than one way to go from one vertex to the other in general in a graph. But when the graph is a tree, no. Also, this other condition that is equivalent to be a tree says that if the graph is connected and we have one edge in the graph, and we take it out, we consider the graph with all the edges minus that one, so this one is disconnected. So what this means? A graph is always connected, but if we delete any of the edges, becomes automatically disconnected. That is something that in general does not happen with graphs, but it does happen with trees. For instance, let's check in the graph that we have here. So if in this graph we eliminate any edge, imagine deleting this one, you see that the remaining is disconnected. If you eliminate any other, it's always disconnected, the result. But in a graph like this one that is not a tree, you see that you can erase this, for instance, and the thing is connected. Right? So this is a property that happens always with trees, that if we have an edge and we delete it, so the graph becomes disconnected. And the other way around is we add one edge. I mean, this condition, what says is that if we add one edge anywhere in the tree, you create a cycle, meaning that it's not going to be a tree anymore. So, for instance, in this tree that we have here, anywhere that we add an edge, here you see the cycle created. Anywhere else where you can think of adding an edge, you will always create a cycle. This is a property that happens only with graphs. In general, if the graph is not a tree, you may add an edge and do not create any cycle. And finally, the last of the properties here, that G is a tree, if and only if G is connected and the number of edges is n-1. So this is a very important property for graph. Sorry, I think that I should have said here somewhere that the number of vertices of the original graph is n. And so what I mean here is that for being a tree, the edges is n-1. I mean, it's always one less than the order of the graph. So, for instance, if you have a graph with 7 vertices, the only way that this graph can be a tree is if it has 6 edges. Let's check this in our trees here. So this tree has 11 vertices. So let's count the edges, we should have 10. And they are, right? So let's count it, are 10. So in this case, the number of vertices was 11 and the number of edges is 10. Will always happen like that in a tree. So if we come, for instance, in this graph, we see that the number of vertices here is 5, right? And the number of edges is 8. You see that this cannot be, just counting the edges and the vertices, you know that this cannot be a tree. And in the first one that we have, the number of vertices here is 5, right? And the number of edges is clearly 4. So when it's a tree, always is dissatisfied that the number of edges is 1 less than the vertices. So check all these equivalences in the theorem in these two graphs.